In this presentation, I will present a procedure to improve the accuracy in the measurement of extreme impedances using an active interferometer. During the presentation, I will first introduce the challenges we face while characterizing extreme impedances. We will then look at what's available in the literature to solve these issues, and I will present our solution and show a calibration procedure. We will then have a look at the experiments we performed, and I will bring you to conclusion. Semiconductor industry is characterized by a continued downscaling of the feature size of the devices. If we look at the NMOS technology, CMOS technology, we see that last year they reached the 7 nanometer node, and by 2020 the 5 nanometer node is expected to go to production. In addition to this, we have new technologies approaching the market like carbon nanotubes, transistor, and nanowires. The ability to further develop this technology is strictly related to the capability we have to model and characterize them. But when the size of the devices approach the few atomic layers and the conductive parasitics are reduced to the minimum, the impedance level exhibited from these devices is extreme. And because of this, it's not always possible to accurately measure these devices with a conventional setup that is usually based on a vector network analyzer. Vector network analyzers have their best performance when measuring impedances that are close to their reference impedance, that is typically 50 ohm. When the impedance of the DUT deviates from this region, the performance decreases, and when we go and measure high reflective devices, like for example something close to an open or close to a short, we can see that the noise level exhibited while measuring the gamma can be up to 2 orders of magnitude higher compared with the 50 ohm measurement. On top of this, the nonlinear relationship within the gamma we measure and the impedance decreases the accuracy of the measurement when the magnitude of the gamma of the device we are measuring is higher than 0.8. We can see here the example of the same noise level measured on the gamma and the effect it has on a 50 ohm measurement and on the measurement of a 1 kilo ohm device. Of course, this problem would be solved if we could shift the sensitivity region of our VNA to a different impedance that is closer to the impedance of the DUT we are going to measure. And of course, this can be done applying interferometry. If we look at the literature, we find several techniques to apply interferometry, and we can group them in 2 main categories. On one side, we have passive interferometers. On the other side, we have active interferometer. A passive interferometer consists of a power splitter and on a well-known reference impedance. This impedance is used to generate a B wave that is going to interact with the scattered wave coming from the DUT. If this is a single impedance, the results will be that versus frequency, there will be a frequency point in which the 2 waves will cancel each other, when the amplitude will be this, when their magnitude will be the same, and when their phase will be opposite. This has a few drawbacks because, on a first place, if you want to have multiple frequencies in which we applied interferometry, we are going to need a mechanical device like a tuner. Second, we will have to use a power splitter, and this is introducing losses on the measurement path, and then is going to reduce the dynamic range of the measurement. Of course, as a pro, it is a really simple setup. On the other side, we have active interferometer. an active interferometer can consist of a coupler or a power splitter and of a second signal source that has to be phase coherent with the source of the VNA. In this way, it's easy to perform gamma cancellation versus frequency, because we can have a B interferometer changing versus frequency. Of course, the phase stability of the cable can impact the gamma cancellation and then the measurement and the calibration. The solution we propose is an HGV mixer-based interferometer. We sample the power coming from the VNA with the sampling coupler. We send it then to an HGV mixer. The HGV mixer can modulate the input signal with the two DC voltages that we call I and Q. The signal is then injected back on the measurement path in order to cancel the B wave that is coming from the DUT. We like this solution because we will use just one port of the VNA, so it's easily scalable even in case we use a PNL, for example. And we saw already that if we perform a 50 ohm calibration and then apply interferometry, we can drastically reduce the noise. In the example, we can see the standard deviation calculated on the real part and imaginary part of the impedance while measuring a high impedance DUT. We can see the blue trace representing the standard deviation of the measurement performed using the VNA. The green trace is representing the results of a measurement performed using a low-frequency interferometer, and the red trace represents the results of the measurement performed using a higher frequency interferometer. In both cases, we can see that we have around 1 order of magnitude improvement in the noise, both on the real part and on the imaginary part. But of course, this is not helping in improving the accuracy of our measurement. The accuracy of the measurement depends, in fact, on the calibration, and more in detail depends on the reference impedance we use as a load during the calibration. If we look at the equation to evaluate the uncertainty of a one-port system, we can see that it has its minimum when the device impedance is the same as the reference impedance we used during the calibration, and grows with the quadratic behavior with the gamma. So, in order to achieve an improvement in the measurement of highly mismatched device, we have to use, during the calibration, a reference impedance that is close to the impedance of the DUT we want to measure. Because of this, the calibration procedure is going to be slightly different than a normal open short load calibration. So we will first connect our high gamma load reference at the section of the DUT section, and then we will perform an algorithm to compute the injection signal in order to obtain at the VNA port the gamma cancellation at every frequency point. Then we store and we keep constant the I and Q values at every frequency point during the whole measurement, because in this way we set the reference impedance of our system to the impedance we used to perform the calibration, that is our reference. Once we have done that, we can measure the short and the open standards . Sorry for this. We will then have obtained a set of error terms whose reference impedance is the reference impedance we used at the moment of the cancellation. Of course, if we want to perform such a calibration, we will need a cal kit with precise and extreme impedances. And for this purpose, a cal kit on wafer was realized on a fused silica substrate, both with low impedances and high impedances, and we extracted the standard parameters through EM simulation. We went then to perform two different experiments to validate the calibration procedure. We performed two high gamma calibration. For one high gamma calibration, we used an high impedance. For the other one, we used a low impedance. To benchmark the quality of this calibration, we performed two 50-ohm calibration, one with a commercial on alumina cal kit and one with a 50-ohm cal kit on fused silica that was realized within TU Delft. To validate and verify the results of the measurement, we used two high impedance standards, nominally 6 kilo and 8 kilo, and two low impedance verification standards with an impedance within 1.4 and 1.55 ohm. To evaluate the quality of the measurement, we evaluate the absolute error both on the S parameter and on the impedance to build a worst case error band. In this picture, we can see the setup we used in our lab in Delft. Here we have the signal coming from the PNA. The signal is sampled and sent to the IQ mixer and is then injected back in this direction to the PNA to perform the cancellation. If we look at the results of the high impedance experiment, we can see that the high gamma calibration presents the lowest error and the constant error versus frequency, while the 50 ohm, the measurement performed using the 50 ohm calibration on fused silica presents a bigger error, and the measurement performed using the 50 ohm calibration on alumina cal kit presents a much bigger error. And we can understand more if we look at the measurement of the 8 kilo ohm standards. We can see here that there is a good match within the EM simulation of the verification standard and the measurement performed with the high gamma calibration. The two 50 ohm calibration presents a similar error while considering the real part of the impedance, but the 50 ohm calibration performed using the ISS cal kit shows a big error on the imaginary part, and this can be maybe due to a low accuracy in the model that is provided from the manufacturer. Looking at the results on the low impedance, we see that still the high gamma calibration presents the lowest error on the gamma. The 50 ohm calibration on fused silica has a similar error, but slightly bigger. Again, we have the same behavior from the measurement performed with the calibration on the ISS. Looking at the error on the impedances, we see that the error both for the two calibration, the high gamma calibration and the 50 ohm calibration on fused silica, is around 0.1 ohm. And this is mainly due to the fact that the contact error of the standards is dominating in this case. And this is not solved when we use a high gamma calibration. In conclusion, we can see that we presented the novel calibration to improve the accuracy of highly mismatched devices. This procedure was experimentally tested using a dedicated on-wafer cal kit and was benchmarked versus conventional 50 ohm calibration. The results show an improvement in the accuracy both on the high impedance and on the low impedance, validating our assumption. That's it. Thank you for your attention.
Thank you. Any questions? Okay. I saw you gave results up to 4 gigahertz. What's the frequency limit on your system?
What we have now in our lab are 2 different interferometers. Basically, the limit is just in the hardware we use. Like if